in high-stakes laboratory and industrial processing environments. A well-optimized chromatography column operates with absolute predictability. Analysts and process engineers spend significant time calibrating mobile phases, choosing stationary resins, and programming precise gradients to ensure reliable separations. However, a truly high-performing column system relies on a flawlessly balanced mechanical environment rather than just chemical formulations. Every physical element inside the column works in perfect harmony. The system delivers sharp, reproducible data for every single run. This helps teams establish clear operational baselines. A top-tier column run consistently balances chemical interactions with controlled physical dynamics, minimizing baseline noise and preventing unexpected peak variations. When a system functions at this level, laboratories experience maximum product throughput, minimal chemical waste, and total confidence in their final analytical or preparative results. The ultimate proof of a high-performing chromatography column is found in its raw data output. Peak resolution represents the column's ability to cleanly separate two distinct target compounds as they pass through the stationary phase bed. In an ideal run, the chromatogram displays tall, highly concentrated, symmetrical peaks that return perfectly to baseline before the next compound emerges. Achieving this requires minimizing spatial spreading while maximizing theoretical plates to keep sample bands compressed. This rigorous efficiency enables reliable tracking. It produces symmetrical Gaussian peaks with an asymmetry factor close to 1 for precise automated integration. It ensures complete baseline separation to eliminate overlapping signals and cross-contamination, and delivers a sharp signal response that maximizes sensitivity for low concentration trace compounds. Ultimately, maintaining these pristine peak shapes removes guesswork by preventing the sample band from warping or widening at the beginning of the resin bed. While peak shapes confirm data accuracy, pressure stability acts as the definitive indicator for column health. During a standard separation run, the mobile phase creates a steady, predictable baseline back pressure. This equilibrium indicates that internal structural boundaries are holding firm, allowing fluid to move through the matrix without encountering shifting resistance. Conversely, uncontrolled pressure fluctuations or sudden spikes signals that the internal geometry is breaking down. If the support structure or internal screen flexes, tightly packed resin beds shift, altering localized density, creating compression zones that spike back pressure, and overwork system pumps. Maintaining predictable pressure stability requires an unyielding, rigid internal boundary that resists micro deformations under continuous physical stress. Utilizing a flat, non-deformable wire mesh screen instead of flexible porous plastic or fragile pressed powder alternatives keeps the boundary completely stationary. This mechanical stability protects the uniform packing density of the resin bed, ensuring consistent back pressure over hundreds of injection cycles and keeping laboratory operations running smoothly. The cornerstone of both high peak resolution and long-term pressure stability is true radial flow uniformity. For maximum separation efficiency, the incoming mobile phase must distribute evenly across the inlet surface the millisecond it enters. To bridge the gap between irregular traditional materials and modern demands, Boker engineered POROSTAR is a multi-layered sintered wire mesh laminate designed for absolute fluid control. Unlike conventional sintered powdered frits with random, unpredictable pathways, POROSTAR is built from individual layers of precision woven wire stainless steel cloth permanently bonded together. This intentional engineering brings complete geometric symmetry to the column inlet, upgrading system performance across key benchmarks. Precise weaving ensures uniform pore geometries identical down to the micron, providing equal resistance to the mobile phase. This balance eliminates preferential flow, preventing the formation of high-velocity channels. Consequently, it achieves laminar flow by neutralizing incoming fluid velocity from the capillary inlet, transforming a turbulent stream into a perfectly flat horizontal sample front. By replacing random porosity with defined mesh openings, POROSTAR guarantees that every molecule travels at the exact same velocity, preventing sample plug deformation to ensure explicitly sharp peak resolutions and highly stable baseline pressures. Thanks so much for watching. If you have any questions, click on our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things Hover and Boker. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.